Okay, I believe we're back. So today, as you can possibly guess from the title, I'm going to talk about Lagrange interpolators. Now, these are sometimes called Lagrange multipliers, but the whole concept of interpolation is a general topic I want to talk about. So first off, I'll explain what interpolation is. Let me get a paint screen up so that you guys can see what I'm drawing. I've done that in the past, and it has not been fun. So let me put this over here, and then I'll get the screen switched up, and we should be good to go. Okay, so a interpolator, that's what we'll start with. So let's start off by explaining when you would use an interpolator. So I'm going to grab, actually, let me get this over here, just so I know that the mic is still working. That's pretty important. Okay, so we're going to put just a bunch of lines. We'll get a x-axis and a y-axis. I said that backwards to what I was doing, but you get the point. So let's say we have a bunch of points here, 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 and here. Now, in statistics, a lot of what you will do is regression, linear regression, quadratic regression. But what you do is you try to find a best fit line. And a best fit line is something maybe like this. So that's maybe a little high. But the idea is it's the average line. Every point is the total distance. If you added up the distance perpendicular from the line to the point, or actually I think that's incorrect. It's the distance in the y value. So like this. That this line is optimized to be as close to all the points as possible. But that's not what interpolation is. So interpolation is a whole different idea. When you have these points like this, and you interpolate those points, you create a function that goes through every single point exactly. So obviously this is kind of difficult to draw, but it should go like that. And then it'll continue on in some crazy manner. And so these functions are nice because if you have exact data, you can get a function that will tell you that will spit back out the exact data when you ask it to. So if you gave it an x coordinate like here, then it'll say this is the y value. And this is very important when you're going into something like perhaps picking out the correct material for a job or how wide you need something to be. If you have something that is properly interpolated through the data points, then you can find the width of that material so that it'll be structurally stable for whatever job you're doing. So this is an idea that is used a lot. Now, the problem with interpolators is as you get more points, if you have a bunch of points like this, in order to get a function through this, you'll end up getting something like this. Just I can't be perfect with that, but it will be this crazy polynomial of super order. So the problem with this is that you have to keep upping the order of the polynomial in order to go through all these lines. But assuming that you have exact data, then you could pick maybe a couple of those points and get an interpolation through there and get it to work out. So, but the specific idea I want to talk about today is Lagrange interpolators. And the reason I want to talk about that is because Lagrange interpolators, although the name, because it has some random old guy's name in it, and then the word interpolators, the name sounds kind of menacing. But on the surface it looks kind of intimidating, and a lot of people might back away from this video right now. But what I want to explain to you is that they are extremely simple. And so basically the idea of a Lagrange interpolator is that it is a switch. So what happens is, let's say we have 3 points. So, or that's probably bad. Let's put one up here and one in the middle like that. And we'll get a value like this. So the idea of Lagrange Interpolator is, like I said, it's a switch. What the Lagrange Interpolator does is it handles each point individually and then adds them together later. So we are trying to figure out what goes here, and what goes here. And so we need to have something that is the value of point 1, so this will be x1, x2, and x3, and this will be y1, y2, and y3. Now those aren't in order, but I want to keep them in order index-wise so that it makes sense when we write out the formula. So obviously any of these could be passed around in different orders, the y values could be different, and this would still work. I'm doing this for a general case. So like I said, the Lagrange Interpolator wants to be a switch, and what I mean by that is when the x value is one of these other points we have, it wants to have a y value of 0. So it wants to be right here. If we're doing the interpolator for the first x value, it wants to be a 0 here and a 0 here, but the physical multiplier itself wants to be the total piece of the puzzle has to reproduce this value. And so what will happen is when we plug in this x value, this guy will be this value, this guy will be 0, and this guy will be 0, because for this one, these two x values reproduce 0, and for this one, these two x values produce 0. So this will be 0, this will be 0, this will be y1, and the answer will be y1. And so that's the idea we're getting for, and it applies to the other ones. If we put in x2, then this one will be y2, this one will be 0, this one will be 0, you get y2. And what is nice about interpolators is it will actually create a function. So we'll get possibly an idea of what's going on in the middle. The interpolators are kind of like a suggestion. They are very good at reproducing the data points, but anything outside of that is definitely an extrapolation, because like I said before, once you get to higher powers, the polynomials tend to be rather spastic. So the point might be correct, but if you move slightly to the side, it could be all the way up here, it could be all the way down here, and that may not make sense for what you're trying to actually have a graph of. So what we need to figure out is what goes in these blanks. So I'm going to erase this down at the bottom for a second, and we'll get back to it in a bit. But we're going to take this one step at a time. So the first step is, well, obviously we have to break this down. So we're going to go top down. We know what the big picture is. What is the next level down? Well, that would be one individual piece of the puzzle. And so we are going to try to create a Lagrange multiplier for the first value, because the entire function itself added together is the interpolation, but these individual pieces are just multipliers. And why it is a multiplier is because it is being multiplied by this y value. So we are going to have some Lagrange value, and so the actual way that you write this out is we have 3 points here, so we want one less order. We want one less order for the Lagrange interpolator. So the first value, if I'm correct, is the order that we have. So this will be a 2, since we want a second order for the 3 points. This probably would have been better. Actually, yeah. So let's start off basic. Let's just go for 1 point. Not 1 point, because obviously interpolating through 1 point would be really easy. You could make anything go through there. But let's start off with these 2 points right here, x1 and x2. And so we want to create, like I said, one order lower, so a first order Lagrange interpolator, and we are going to do it for the first unit. So since I used these indexes 1, 2, 3, I'm going to put 1 here, but a lot of times people will start off with a 0 as the index. So if you see that, that's what it means. It's the 0 is just the first value there. So we need to create a Lagrange multiplier that is first order, meaning that it only has x to the power of 1. It doesn't have x to the power of 2 anywhere. And it is going to be a switch that turns on when the x value is x1 and turns off when the x value is x2, since we're only focusing on these points right here. So how do we do that? Well, the switch obviously needs to be 0 when it is x2, and it needs to be 1 when it is x1, because if it's 1, then we can just simply multiply it by its y value, and we reproduce the y value, because anything times 1 is itself. So the way this is going to work is we're going to have a fraction, actually. So, okay, well, first off, how do you make something 0 at a certain point? Well, if we have our x value, which is the variable 1, and then we subtract away this constant, which is x2, then if we plug x2 into this, we get 0. But what happens if we plug x1 in? Well, that's x1 minus x2, and judging from this, it would be a negative number, but in the general case, it will be some number that might possibly be 0, it might possibly be 1, but we don't know. So we need to set this up in a better way so that it is always 1 when we plug x1 in. And so like I said previously, we do this by making it a fraction. And so when we plug x1 here, we want the bottom to divide it so that it equals 1. So how do you do that? Well, the way you do that is you divide it by itself. So we want this to equal 1 when it's x1 minus x2. So this is our first order Lagrange multiplier. So we can go back and check this. If we plug in x1, then it's x1 minus x2 over x1 minus x2, and the answer is 1. And if we plug in x2, then we have x2 minus x2. That's already 0 on top, and 0 on top of a fraction is 0. So then we have a switch now, and it switches on when it's here, and it switches off when it's here. And so that's the idea. So then what would happen is if I go in and erase this to give me more space, let me get a bigger thing to work with. That's not too much better, but it'll work. All right, so we're going to get a little bit more space here. Okay, so to come back to the final product, what we do is, since there's only 2 points here, we're going to have 1 plus sign. We're going to have, so this will be some function p, and these are our 2 blanks that we have to fill in. So we already know what this one is. This one, I'm just going to use these as the fractions. So this is x minus x2 over x1 minus x2 times y1. And then we have the inverse of that, or not necessarily the inverse, but the converse of that. So we have x minus x1, and then we have x2 minus x1 on the bottom. And this will be multiplied by y2. So let's check this. When we have the value as x1, we plug it into here. This becomes 1. And so 1 times y1 is y1 plus and then we plug in x1. x1 minus x1 is 0. This becomes 0 times y2 is still 0. So the answer is y1. And then in the other case, this becomes 0 because x2 minus x2 is 0 times y1, which is still 0. And if we plug x2 in here, we get 1 times y2 is y2. So this works. But how do we kick it up a notch? Okay, so now I'm going to just clear the slate. It's easier than sitting here and erasing it. But we'll redraw a graph in here with our 3 points. And we have our x1, x2, x3, y1, y2. That's a little bit lower than that. y3. And so now we have 3 points. What this means is we need a Lagrange interpolator. And by the way, this is just an L. It's just a fancy L. We have our Lagrange interpolator. It's a second order now. And let's just do it again for the first point. So what do we need to do now? Well, it's the same basic concept. And I bet you can probably guess from now how we would do this. Let me pull up the chat to make sure. Okay. You can probably guess how we would do this. And so the way that we do this is we do about the same thing. We create a large fraction that is a switch, but this time we need it to be 0 in 2 different places and 1 in only 1 place. So the way we do this is we have we're going to have 2 things to work with on the top here, and the same on the bottom. So the first one will be what we wrote down before, x2. So this, and remember, we're working for x1 here. We want it to be 1 at x1. So then, so we also want it to be 0 at x3. So x minus x3. So then when we plug x3 in, this term becomes 0. It doesn't matter what this is because 0 times anything is 0. And it doesn't matter what this is because then it will also, it will already be 0. Assuming that none of these values are the same x value, but then it would become confusing because you can't make a function where one x value has 2 different y values. So that would be interesting data to try and work with. But so then we have our off switches set up, so we just need to create our on switch. And the way we do that is with the same logic. We need to create a scenario on the bottom that will be the same as the scenario on the top if x1 is plugged in. So x1 minus x2 and x1 minus x3. And it's a good point to note that these are all just constants. So what will happen in actual practice is maybe if this is 1, 5, and 9, then you can plug 1, 1, 5, 9, and do the math here. So this would be what? That would be negative 4. This would be negative 8. Negative 4 times negative 8 is 32. And so you'd have 32 on the bottom. And so then it simplifies down to something that's workable. You could even multiply this together. Now that gets a little bit stupider because it's harder to see the zeros. So it's better to keep this spread out on the top because then you know when it turns off. But having 32 on the bottom isn't that bad. So this is what we were looking for. When you plug in x1, you get the same thing you have on the bottom on top, so it multiplies together, or it divides and becomes 1, and then you have individual pieces on the top that when the other x values are plugged in, the whole thing becomes 0. And so what happens is you do the same thing. You have some function p where you have your x minus x2 times x minus, not x1, x minus x3 all over your x1 minus x2 times your x1 minus x3. And so this will be multiplied by y1, and you'll have the same thing for the other terms. And this can go on for as many values as you want. But like I said, if you get to too high of a power, then you will be creating a polynomial that will be very spastic in nature. So you won't really get the idea that you're trying to go for. But what this is actually doing is it's tracing parabolas. So it's creating what's happening is for here, for the first value, this function that we've created is going to be, I'm actually going to clear the slate because it'll be easier to draw with nothing on the board. So let's get a big graph, and I'll use some different colors for the different graphs. So we have our x1, x2, x3, then we had our, okay, I'm going to just put one thing here. This is the value 1, and this is 0, obviously. So, like I said, this is a second order Lagrange interpolator. So I'm going to grab a red pen. So we want this, this function to be 1 at x1, 0 at x2, and 0 at x3. So what kind of function will go through here? Well, I said it's a second order interpolator. So if you can imagine, that is x squared. So we have a parabola that goes through here, continues downwards, and it won't be as linear, so I should probably try and make this a little bit better. But it's going to curve downwards, and then it'll hit 0 here, and as parabolas do, they come back up and continue onwards in this direction. So this will be the multiplier that we have for x1. Now for x2, I'm going to grab green. We want x1 to be 0, x2 to be 1, and x3 to be 0. So you can probably guess where this is going. We just have an upside down parabola that obviously it can't match up with this being the center because this is longer than that, but it'll be something that looks a little bit like this because it will go a little bit higher than 1, but it will achieve 1 when it hits the x value of x2. And so we have that, and then I'll grab a blue pen for the last one. So once again, we want x1 to be 0, we want x2 to be 0, and we want x3 to be 1. And so this will be similar to the red one, just in the opposite direction. So we're going to draw something like this, and then it will extend upwards and go through this point. So these are the three functions that are the multipliers for this value. But as we said before, they are being added together in a linear style. So we'll have our blue one plus times our y3, and then we'll have our green one, so that'll be plus our green one times y2, and then we'll have our red one. I didn't draw the plus sign again. Our red one times our y1. And this will all equal our function p. So this is what's happening behind the scenes. And so it's pretty simple when you boil it down. And I'm actually pretty happy with how the graph turned out. I think that's a good description. But you can imagine, so we're multiplying by these y values. So this is going to be blown up to where this value is whatever y value it actually was, and this value will be here and or like here, and what was this, like there. So what's going to happen is it's going to create a parabola of sorts that goes through all of these. So it will actually look something like this, in a sense. So it will still be second order because we're having a x squared term plus an x squared term plus an x squared term. And so x squared plus x squared is just x squared times a larger number, unless it's a negative number. But so it will create this larger parabola that actually hits every point where we want it to because of these multipliers. And so that's the idea of a Lagrange interpolator. So that's pretty much it. It's fairly simple, and I actually did bring it up in the episode I was talking about my addition to the coding project with data mining. I threw a Lagrange interpolator into the mix because I wanted to see how the AI would handle something that switches on and then switches off to simulate a conditional expression. So that's the idea, and I'll probably be integrating it into the physical code. So as opposed to using if statements, I'll just create something that creates a Lagrange interpolator, because a Lagrange interpolator also has some answer to this area in between, as opposed to simply a switch on or a switch off. So that allows some possibility for reaching outside the lines of what data you actually have, but at the same time, it does bring up the possibility of the horrors of extrapolation. So it doesn't necessarily go for that perfect. It's not perfect in nature because it can have those crazy jumps back and forth in between. So maybe I'll put conditional statements and Lagrange interpolators in there, but we'll see. It's always fun to just see what the AI comes up with. But that's pretty much what I wanted to talk about on Lagrange interpolators. So I hope that you have understood what I've explained here. If you have any questions, please leave them in the comments on the video once it's uploaded. But for now, I'm going to be moving on to my random drawing section, which, as you will have heard in the beginning of the episode, I have a brand new sheet of paper with random terms on it, so I'll be using that, so that's exciting. I'll be playing a quick ad while I run to get my calculator and everything set up, and I will be right back.